Today we're going to take a look at 7.6, which is moments, centers of mass, and centroids. The first thing we're going to do is we're going to define what is meant by the word mass. Mass is a measure of a body's resistance to change in motion. It's independent of the gravitational system that you're in. Sometimes it's equated with weight, though this is not technically correct. This is a type of force, and it's related to force by... How is force related to mass? Do you guys know this one? All right, so force equals mass times acceleration. Right, which would be gravity in most situations. On page 486 of your book, there are some commonly used measures of mass and force and their conversion factors, so you might need those in particular problems or whatever to look at. Or maybe you've already got them memorized because you guys are so fantastic in physics. I don't know. But those are on page 486 if you need to reference them. All right, the first kind of center of mass that we're going to talk about is very basic. I can even draw the picture. It's that basic. So the first one we're going to look at is the center of mass in one dimension. So a moment of mass is a measure of the body's resistance to an object's ability to resist rotational change. Depends on the mass of the object and its distance from where the object is being moved. So the moment, I usually have these typed already in here, but I don't for some reason today. The moment of mass is mass times the length of the moment arm. Another way of writing length of the moment arm is the distance to the fulcrum. So we end up with something that looks like m times a distance x. Okay? Here's the picture you want to have in your mind. You want to picture a teeter-totter. Can you picture a teeter-totter like on the playground for the children, right? When you are too heavy on one side versus the other side, it goes down, and it makes it very difficult to teeter-totter with a child, right, if you're way much more than they do. So maybe they've got two of them on one side and you on the other side. Or something else that you might do is you might move where you are so that you're not on the very end of the teeter-totter, you're further in on the teeter-totter, that thing. I mean, that kind of a thing. So the distance to the fulcrum would be the distance from where the weight is, the person's weight is, to the center where it's actually balancing. Okay? That's the distance that we're talking about. So if you take a look at the example, that's exactly what we're going to be doing. We're just not doing a teeter-totter, we're doing a guy on a rock. But consider a person weighing 200 pounds, sitting on one end of a 5-foot beam. He has a 600-pound rock he needs to lift. Now, lifting that rock with his own arms would probably be a bad idea, right? He's probably going to hurt himself if he can even do anything with it at all besides go, and just not move it, right? Okay? So the question is, where must he place the fulcrum in order to be able to lift and balance the rock with his weight? So the picture you have is, again, it's like the picture of the teeter-totter. We have our guy over here, and he's 200 pounds. And we have our rock over here, and our rock is 600 pounds. And our question is, where would this center point, I use the word center not because it's halfway, but because it's somewhere between them. Where would this center point, this fulcrum, have to be in order to make this a balanced weight distribution? Obviously, it's not halfway because they're not equal weights. You guys with me? So what we are going to do is, and it tells you that the full length of the beam is actually 5 feet, right? That was one more piece of information. Did I get everything written down? Okay. So what we're going to do is we're going to let one of these distances be x, and then what would the other distance be? 5 minus x, exactly. Okay, that part kind of feels like the radiuses that we've been doing, honestly, right? We've got a full length of 5, and then we've got 5 minus x. This formula that we have back here, albeit a very simple one, says that our moment equals mass times the length of the fulcrum. So the mass, or at least a version of it that we can use in our situation, because they're both given in terms of the weight. On the gentleman, he is 200 pounds, and he's at a distance x from the fulcrum. The rock is 600 pounds, and its distance is actually 5 minus x from the fulcrum. And we're going to solve a very simple system of equations by doing this, right? Absolutely. So I have 200x equals, what's 600 times 5? 3,000 minus 600x. Can add my 600x to the other side, so I have 800x equals 3,000. And if I divide, what is 3,000 divided by 800? 3.75, and this is measured in feet, right? So 3.75 measures the distance from the fulcrum to where? The man, right? It's the man, the fulcrum to the man. Because if we want to say 3.75 feet, we need to clarify, because we've measured two distances in terms of our picture. So this is 3.75 feet from the fulcrum to the man. Okay, so that wasn't calculus, correct? No, that was algebra. Okay, so we're starting there. We're going to develop it further. We've done that in a lot of our situations where we started with something you've seen in an algebra or trig sense, and then we've developed it further. So what we're going to do next is we're going to generalize this to having multiple weights along the beam. We had two in this case. We had the guy and we had the rock. Okay? But we could have multiple weights along a beam. So now imagine like a ruler. There's usually one in here. I don't see one today, of course. So imagine a ruler. Pretend this is a ruler. And you put different weights of things along here. Maybe they're different weights of pieces of candy. Okay? And they're at different distances apart. There's still going to be some place in between where I can balance this, and it's based on all of those individual weights of the individual candies and how far away that they are from that balancing point. Okay? So no longer do we just have two, we have, I don't know, kind of, a lot. We don't have a specific number, it can go further out. So we can generalize this idea to multiple weights along the beam, and we see that, oh goodness. Let me write down what the moment would be on this one. Moment would equal each weight, so M1, times its distance x1, plus M2, the second weight, times the distance x2, and all the way up until we get to whatever our last value is, and they're calling it M sub n with a distance x sub n. Okay? That's what our moment would be. And the moment, the points when the moment is 0 is called the equilibrium points, that balancing point. For a system that is not in equilibrium, the center of mass is the point x where the fulcrum should be located to create equilibrium. Okay, that's what we've been talking about, this idea of creating this equilibrium. So I think it's not written on the next screen, yeah. Let me write it in here as well. So this equilibrium point, this balancing point we're going to call x bar, would be, and this notation might be a little bit foreign to you, so write it down first and then I'll explain the notation in case you haven't seen it. Sorry, my letters are so small, but the letters underneath the funny kind of E shape, it's actually a sigma. It says I equals 1 to n. This one also says I equal 1 to n. This is m sub I, x sub I, and this one just says m sub I. Okay, that top right there is the exact equation that we had above. So this is the mathematical notation for this equation right here. This is the sum from I equal 1 to n of m sub I x sub I. So this notation, this sigma notation means sum. Okay, it means you're adding a bunch of things together. And what you're adding together is you're adding together pieces that look like m times x. And that's exactly what we'd written out above. M times x, m times x, m times x, and we're adding a whole bunch of them together. And then in the denominator, what we're doing is we're dividing by what? Can you tell me what that looks like it is based on what we just talked about that notation meaning? Yeah, the sum of all the masses. If you were to just add all the masses together, right, this is like what you do when you divide out and figure out your grade in a class, right? You take the grade that you made times how much it's worth, and then the grade you made on the exam 2 times how much it's worth, and the quiz 1 and the quiz 2 and the homework this and the homework that times how much they're worth, and then at the end you divide total by the number of points in the class. That's actually what this is. Okay, so this is one way of doing this. So I'll write out in words what we just said. This is the moment of the system divided by the total mass. Of the system. Okay, so we're going to take what we did in the previous problem a step further, and we're going to do one that's got multiple masses now and multiple distances. Okay, so this is still not calculus, all right? I promise we're going to get there, but this is another problem that just extends this idea one step further. So we're going to find the center of mass of the point masses lying along the x-axis. M1 is 12, M2 is 1, and so forth, and then all the x distances away are listed below. All right, so what we're going to do first is we're going to need to find two things. We're going to need to find the moment, and the moment is found by taking each of the masses times its distance along the x-axis. So 12 times negative 6 plus 1 times negative 4 plus 6 times negative 2 plus 3 times 0 plus 11 times 8. What do we get? Somebody said it. I got 0 as well. It's okay. Did you guys get 0? Okay, good. You're not always going to get 0, so I'm going to show you what we would do next, particularly if you didn't. You would want the sum of the masses. Technically here you wouldn't need this one because you've got a 0 already, but if you were doing the sum of the masses because you didn't have 0, you do negative 6 plus negative 4 plus negative 2 plus 0 plus 8. Oh, thank you. I'm on the wrong line. I appreciate that. Yeah, we don't want negative masses. That would be weird. All right, 12, thank you, plus 1 plus 6 plus 3 plus 11. What's that give us? How fast can you guys count? Yeah, it's 33. And then the moment that we were looking, or the x bar, the equilibrium point that we were looking at, should take the moment divided by the masses. That's why I said this one doesn't really need the masses to find it, because it's just 0. It's already in equilibrium, right? That's what this tells you. The equilibrium is already achieved. So if you set up, in lack of better descriptions, a ruler, and you had the location of the ruler is halfway, is the equilibrium point 0 in the middle, okay? And you put masses of 12, 1, 6, 3, and 11 in whatever unit you're working with. At these particular distances, it would be at equilibrium already. Okay?
I have a question.
Yeah.
Is that like where we get 0 at the answer?
Mm-hmm.
Would that be a weight or would that be a distance?
That's a distance. It's the average distance in this case from would be the y-axis, from like where x equals 0. So this one would be actually on the y-axis if you think about x, y-axis coordinate plane. Mm-hmm. Yes, you can put the fulcrum exactly in the middle, right?
So if you get a negative, does that be left, positive, right?
Yes, it would be. Mm-hmm. Yeah. Okay, that was center of mass in one dimension. So now we're going to do center of mass in 2 dimensions. So imagine balancing objects with a mass on a 2-dimensional shape. Example, 2 blocks on a plate. We're still looking for the place or the point at which the objects will balance, right? and we're going to watch a short video clip. Are you guys ready? Okay. Okay, so in the clip of the National Treasure, there is a point where they're standing on what we would be calling, in this case, this two-dimensional object. It's not exactly a two-dimensional object, but it's serving the same purpose. So we're examining it kind of like we're examining a plate, and the idea that they want to keep it balanced so they don't fall off. All right, so they keep moving around to try to keep this thing in some kind of a sense of balance so that they don't end up dying. So what we're doing in our center, when we do this with 2 dimensions, is we have to do the moment about the y-axis and the moment about the x-axis. So the moment about the y-axis and the moment about the x-axis individually look very, very much like the equations that we saw earlier for the moment all by itself. Yeah. So take a look. The moment about the y-axis, m sub y, is actually each of the masses times the x distance. And the moment about the x-axis is each of the moments times the y distance, or each of the masses times the y distance. But then when you find the center of mass, also known as the center of gravity, the x average, equilibrium average, is actually the moment about the y-axis, m sub y over m. And the x average is the x part of the center of gravity is the moment around the x, so m sub x divided by m.
Why do they do that?
It does. It feels very awkward. I don't know why the notation is done in that way.
You could just switch it. It makes more sense x with x.
Yeah. This is the notation that your book's using, so I'm going to use it just for, otherwise you're going to end up looking at a book and you're going to be like, well, now I don't know which one to use because they don't match. And this is the common notation used too, so it's not just like your book. If you were to Google it or something or look at another textbook, it's going to match this as well. It is, I agree. All right, so we're going to take a 2-dimensional version of this now. We've got all of these masses, 12, 6, 4.5, and 1, and 15. And then we've got the xy ordered pairs. Okay? So we need to find m sub x, m sub y, the total mass, and then we're going to find the equilibrium point that we've been measuring. So we'll start with m sub x. So we take the mass, and we multiply it by the, as Evan was noticing, the y values. We use the y values inside of this. We take the second mass, 6, times the y value of 5. Third mass is 4.5, times the y value of 8. And then our 15 times our y value of -2. So grab your calculator, do some multiplication, some addition and subtraction, so to speak, and tell me what you get for m sub x. $72 is correct. Now we're going to find m sub y, found much the same way. Each of the masses will still be there, but now we're using our x value, so 12 times 2, 6 times -1, 4.5 times 6, and 15 times 2. Oh, okay. So you really wanted to bring it and let us see it? I'm going to have to check out Netflix and see if we can find it. I think that's a good idea. All right, what did we get? I think Caleb got it. What'd you end up with, 75? 75 is right, yeah. All right, we also need the total mass, m, and that's just adding all of the 4. There's only 4 here masses together, so 12, 6, 4.5, and 15 for a total of what? 37.5. And then to find the equilibrium point x bar and y bar, we find x bar is m sub y over m, and y bar is m sub x over m. So m sub y was 75 over our total mass, which was 37.5. And m sub x was 72 over our 37.5. So what do we get for x bar? That one's 2. And y bar is almost 2, but not quite. What is that one? It's 1.92. And so the center of mass, that equilibrium point we're talking about, is x bar, y bar. So it's 2, 1.92. So in terms of our xy plane, we would have to balance this at the x value 2 and the y value of 1.92 with all of those weights in those locations, and we would have a perfectly balanced system. Okay? So, no, that was still not calculus. I know you were kind of hoping, but we're almost there. The next thing we're going to look at is a planar lamina. Okay, so let me first tell you what that is. Consider a thin, flat plate of material of constant density. Okay, so if you want to imagine, you know, like a plate itself, mostly plates have the constant density. That's okay. We call that a planar lamina. Density is a measure of mass per unit volume, but for a lamina, it's mass per unit of area because it's flat. Notated rho. So that's a Greek letter rho. It kind of looks like a P, scripty kind of P. And then for an irregular shaped lamina, the mass M is equal to rho times the integral from a to b of f of x minus g of x dx. This is rho of A for the region A, for the area A of the region. Okay, so that's our mass. And now you saw calculus, because there's an integral there, right? I know, an integral there, so it's awesome. M is mass, yes. We're using that lowercase m for mass. Okay. So imagine what we had done in section 7.1. Remember we were finding area between curves, right? Yes? That's the formula you see on the inside of this, right? F of x minus g of x dx from A to B. You're finding the area between two curves. And you're multiplying it by the density, rho, and that will give you the mass of your planar lamina, of this sort of irregularly shaped object. Doesn't have to be a rigid square like we were doing in the xy coordinate plane, or a line segment that we were doing in one dimension. We're doing this in an irregular shape now. So what do we do for the center of mass for this irregular shape, this odd shape that we have? We're going to let f and g be continuous functions, where f of x is greater than g of x. Okay, that's exactly what we did when we were doing the curves that we were doing in section 7.1. On AB, and the density of the planar lamina is, I don't know where my eye went, but is rho, bounded by y equals f of x, y equals g of x, and goes from A to B. All the notation that we used in the previous screen, actually. The moment about the x-axis and y-axis are given by m sub x and m sub y. So these formulas look very much like the formula for mass on the previous screen. They've got rho times the integral from A to B. But what happens next is different. So on the first one, we have f of x plus g of x divided by x times the f of x minus g of x. And then we have dx, of course. And then for the moment around y, we have x times f of x plus minus g of x, times the d of x. Now, finding the center of mass is found the same way as we did it in two dimensions. You find x bar by taking m sub y over m, and y bar by taking m sub x over m. And again, I've got it written here too so that you can see it, where m is rho times the integral from A to B of f of x minus g of x dx is the mass of the lamina. All right, so we're going to do a couple of examples. One example of this and one example that's going to change things up just a little bit. Sorry, you're still writing? Okay. Is anyone else? Seth, you're still writing? It's okay. Jaden. I would encourage you on the next sheet to write small. I know, it's a whole sheet of paper, but let me show you. This is my whole sheet of paper. Okay? We're going to write a lot. So write small and write neatly. All right? We're going to find m sub x, m sub y, so that we can, and the mass m, so that we can find x bar and y bar. So our laminas of uniform density rho, and they're bounded by y equals negative x squared plus 4x plus 2 and y equals x plus 2. Now, in order to do this, we have to draw the graph. So grab your calculator and find out what the graph of y equals negative x squared plus 4x plus 2 and y equals x plus 2 look like. And in particular, what you're looking for is since those are the only two curves they give you, you're looking for where they are bounding one another, where they cross. Okay, so one is a graph of a negative x squared, so it's a parabola opening downward. The other one is a graph of a line, and the graph looks something like this, and this. Is that a fair estimate of what your picture looks like? Okay. Which graph is on top? F or, I'm sorry, which graph is on top? Which one is going to be our f of x? The parabola. So the x squared graph is on top, and then the y equals x plus 2 graph is on bottom. The region that we're looking at is the region inside of here, right? This is our planar lamina, that blue shaded in piece. So which would you like to find first? M sub x, m sub y, or just little m, the mass? M sub x? Okay then. We're going to find m sub x. I think that might be the hardest one. Yeah, probably is. All right. Yay. So m sub x is supposed to take our formula's over here, rho, which we don't know, times the integral from a to b. Well, what is our a and our b?
0 to 3.
And how did you get 0 to 3?
X values where it intersects.
The x values where it intersects. So this is important information, those intersection spots. It's going from 0 to 3. And we need, and according to this equation, to take f of x plus g of x over x. So we need to add our two equations together. So negative x squared plus 4x plus 2 plus x plus 2 all over 2, right? Are you guys okay with me putting the 2 out front with rho? Is that okay? I think that's a typo. I think that's why. I don't think that's supposed to be x. Yeah, it's a typo. I'm sorry. It's like, I know there's a reason. That's a typo. Please fix that one. That should say 2. My bad. That's much easier to do with. Who likes a 2 better than an x? Me. I do. Okay, fix the error, please, please. That's what happens when you're typing things in. Errors happen. That one should be a 2. So over here, it would be much friendlier, in general, to have rho over 2 at front. Or you could even change your equation to represent it that way if you'd like. Okay, so we've got this expression added, and then we're going to have the same expression subtracted, right? Negative x squared plus 4x plus 2, oops, minus x plus 2 dx. This is calculus with a lot of nitty-gritty algebra in the middle, right? Really is. It's messy. All right, so let's simplify, clean things up, and see what happens. So we've got rho over 2 times the integral from 0 to 3. If I add these together, I have negative x squared plus 5x plus 4. If I subtract them, I have negative x squared plus 3x. Is that what you guys have? I think that's what I have on my paper. Okay. What do I have to do next? Yeah, a lot of multiplying, right, Seth? You're going to have to distribute this out. So every term in the trinomial has to be multiplied by the terms in the binomial. The way that I do that is that I do it piece by piece. So I take this first term and multiply it by everything in the second set. So I've got x to the 4th minus 3x cubed. And then I'll take 5x and do the same thing. Now I've got negative 5x cubed and positive 15x squared. And then I have the 4, so I have negative 4x squared and positive 12x. Okay, pairing things up, I've got x to the 4th minus 8x cubed plus 11x squared plus 12x. Is that what you guys have? Fantastic. Can we integrate that? Well, of course we can. We're over 2. All right, so I have 1/5 x to the 5th. I have 2x to the 4th plus 11/3 x cubed plus 6x squared. Fantastic. That's what I have written on my paper as well. We're evaluating at 3 and 0 is like our best friend ever for evaluation purposes. At least when we're doing polynomials, it is. So we have 1/5 times 3 to the 5th minus 2 times 3 to the 4th plus 11/3 times 3 cubed plus 6 times 3 squared. And then all of that technically minus 0. All right, what number do you get with all the mess? Either in fraction or decimal form on these will work fine, as long as the decimal is ending, terminates. This one will. Are we having a hand cramp there, Levi? Yes. No calculator today, Nate? See several of you putting it in the calculator. Kay's got 2 calculators, so she might be willing to share. She's a chemistry person, so she has to. Oh, I see. Okay, is anybody close to getting a value? Neither of those are what I have. That's not good. Try again. Yeah, we don't have row. Oh, you know what? I already have my number divided by the 2. So I think one of your answers actually is what I have. Because I didn't have the row or the 2 in my answer. 19.8. Yeah, that's what I have. 19.8, or if you do it as a fraction, that's 99 over 5. So this is 19.8 row. Okay, everybody okay with that? Sure. That was m sub x. We also need m sub y. Let's do that one next. M sub y. Yeah, 19.8 and then times the row that's still there. We'll talk about that on Thursday. Okay? M sub y, are y'all ready? M sub y is row times the integral 0 to 3, same values we had before, and this x really is x. It's not a 2. I did not make a mistake on that one, sorry. It is x. Times the integral, or times the difference of the 2, so it's negative x squared plus 4x plus 2 minus the x plus 2. Why is the integral the same? Yeah, it's still in terms of x. Yeah, it's still dx. We're looking at that one. Okay. Okay, and we already did that subtraction once. We found out that it was negative x squared plus 3x dx. We actually have to multiply that now by x. So I have negative x cubed plus 3x squared dx. All right, antiderivative time. What do you get? X to the fourth over 4, plus x cubed, and we evaluate at 3 and 0. Again, have that evaluation of 0 being awfully friendly for us. So I have negative 3. Hang on, be really careful how I'm writing this. I have negative, and then I have 3 to the fourth over 4 plus 3 cubed. And then technically minus 0. You don't have to write the minus 0, but it's there. All right, so grab your calculator and find out what is 3 to the fourth over 4, and then make that negative plus 3 to the third.
Negative 11.25.
I don't think it's going to be negative.
Yes, 27 over 4, or 6.
Yes. I'm going to put mine in decimals just for this time. 6.75 or 27 over 4. Row. Did you get it to work out, Abby? You're just checking still?
Still thinking about
Are you putting the negatives on the exponent? I do that all the time.
You did 3 to the fourth over 4. Oh, you did plus 9. This would be plus 27. 3 cubed.
Oh, okay.
Yeah, that's okay. We got it. Okay, so this one's m sub y. What else do I need? Don't everybody answer at once. I need m, right?
Yeah.
I need the total mass. Okay, so the total mass is rho times the integral from 0 to 3 of the f of x minus g of x. So that's this negative. Again, you don't have to write this out exactly. You can write the simplified version if you want, since we've done it twice. But it's negative x squared plus 4x plus 2 minus the x plus 2 dx. So there's no over 2, there's no adding a, or multiplying by an x or multiplying by f of x plus g of x. I just have the negative x to the fourth minus 3x. I don't mean fourth, I mean 2. Yes, and I do mean plus. Thank you. We'll get it written down right eventually. Negative x squared plus 3x is what I want. All right. Antiderivative. What's negative x squared? Negative 1/3. I'll write it the way you just said it. X to the third. And then plus 3/2 x squared, right? Evaluate 3 and 0. So this row is negative 1/3, 3 cubed, plus 3 squared, or 3/2 at 3 squared. And then again, technically minus is 0. So what do you get when you simplify everything with a 3 plugged in on that one? It is, it's 4.5. 4.5 row. We're almost done. We are almost done. Almost, almost. We need to find x bar and y bar. X bar is m sub y over m. What was m sub y? 6.75 row over m, which was 4.5 row. What do you notice about the rows? They cancel out. Did we really need to know what row is? Not in the slightest. All right, so what happens when I take 6.75 and I divide it by 4.5? 1.5 is correct. Good. Now we're going to do y bar, which is m sub x, the moment of x around, or m sub x divided by m. And m sub x we had was 19.8 row over the same 4.5 row that we just used above to give me what? 4.4. And our moment, or our center of gravity, or center of mass, is 1.5, 4.5, 4.4, sorry. It would be a good idea to take a look at your picture and make sure that that's actually inside of it, don't you think? It would probably be wise. So just take a gander real quick at your graph. I didn't do it on my calculator, but I did it over here. My graph does not have my y coordinates actually labeled. But we did have it between the x values. That makes sense, right? It is between the x values of 0 and 3, and it's actually halfway, which is interesting. It wouldn't have to be that way, but it is. It was 1.5. And then your y values is 4.4 in between the y values that you see on this particular graph that I've got shaded in blue. Yeah, it is. So this actually works, okay? I have one more definition, and we'll just talk briefly about what we're going to do with the last problem, and then we'll do it next time, so we'll push the quiz that we have into next Monday, okay? Or next Wednesday, Tuesday. Every time I say Monday and I mean Tuesday, I move say Wednesday next. All right, the last thing we're going to do in this section is called the centroid. That's good because our title for our section included the word centroid and haven't talked about it yet. The centroid is the center of mass of a region with a constant density, rho equal 1. So you calculate x bar, y bar with rho equal 1. Straightforward. Yeah, you just don't have a rho in there. Okay, that's a centroid. Constant density, rho equal 1. That's all it is. All right? I want you to take a look at this next one that we're going to do. What I'd like to look at before we leave today is what this shape actually is. It looks like a very complicated formula. In fact, you see A's and B's in it. And you might be even looking and go like, what am I going to do now that I've got A and B in there? I mean, I don't have a way to actually even put this in my calculator. I can't even graph it. And you're right, you can't. You can't put A and B in your calculator. You have to put numbers. A and B are sort of arbitrary here. What's going on? Well, let's just take a real quick moment to actually solve this where I get the x's and the y's on the same side and see if it starts to look familiar, like a formula you have seen before. So the first thing I'd like to do is to multiply by the b over a. I'd like to move it out of the way, okay? Or multiply by the a, I should say it that way. So you're also going to have a lot of writing on this page, okay? So write small, maybe like on one side or the other. So this is ay equals b times the square root of a squared minus x squared. What could I do next to simplify this equation? We could divide by b. How about instead, because then we'll just get fractions, and I'd kind of like to not have the fractions, let's square it next. So now I have a squared y squared equals b squared times a squared minus x squared. And I can multiply 3 by b squared, right? Sure. A squared y squared equals a squared b squared minus x squared b squared. Then I'm going to move the x on the other side. So I've got x squared, or I'll write the b first just so that I've got the constant in the front. B squared x squared plus a squared y squared equals a squared b squared. Lots of squareds. What fun. I'm not going to take the square root because then I'll get the square root back involved. I don't really want a square root involved for the purposes of identification here. But I am going to do something else that feels like it's not going to be very helpful, and it will, in fact, turn out being very helpful. I want to divide by a squared b squared. Every term. I know, I just told you I didn't want to do that, and now I'm telling you I do. Typical, right? Changing my mind. Tell you what. Yes, it will. This is x squared over b squared plus y squared over a squared. I think I just wrote this backwards. I did. Thank you. X squared over a squared plus y squared over b squared equals 1. Does anybody remember what this is an equation for? Yeah. Say that louder for me, Caleb. This is an ellipse. This is the equation of an ellipse. So now that you know that it's an equation of ellipse, you know what an ellipse looks like. Where is this ellipse centered? The origin. And the reason I know is because the x squared is just simply x squared and not something like x minus 7 squared. And the b squared, or the y squared, is simply y squared, not something like y plus 2 squared. So this is centered at the origin. An ellipse looks something like this, right? An elongated circle, if you will. The values underneath x and underneath y tell you how far out you go. They act kind of like radius acts. So this distance out here is the distance that you go in the x direction, and underneath the x we have the variable, or the number, if you will, a. So this is distance a. And here you have the distance b. Okay? So this shape itself, when we're shading this in, goes from negative a to a along the x-axis. And we will be using that information along with rho equal to 1, because we talked about that already with centroids, rho equal to 1, as we find m sub x, m sub y. The piece that we're going to find before we leave is we're going to find little m, because it doesn't use any calculus. If we were to set this up for little m and we were to use the formula, that is to find the area of this shape with calculus, you don't have the integration tools to do that yet. Okay, so like if I set this up and I said, okay, we're going to find, we know rho is equal to 1, I want the integral from negative a to a of b over a times the square root of a squared minus x squared dx. That's what I would physically have to do with calculus. The problem is you have an x squared underneath a square root, and u substitution isn't sufficient on this particular one. You're going to get to use substitution on m sub x and m sub y, but it won't be useful here. So I can't do this right now. I don't have the ability to do this. So no tools yet. Very soon, chapter 8, it's coming, but not yet. So any idea how we find the area then, think geometrically, of an ellipse? What is it? Okay, you're thinking along the right lines. If this were a half circle, right? And so the radius r is here and the radius r is here. It's 1/2 of pi r squared. Right? Because it's half of a circle. Formula for area of a circle is pi r squared. This is 1/2. Why do you think it's r squared? Yeah, both of these lengths from the center out are the same length r. So what do you think it's going to be for an ellipse? 1/2 pi ab, because the distance out is a and the distance out is b. So our mass of this object is actually 1/2 pi ab. We didn't do it using calculus, though. We did it using geometry. Okay? The other ones we'll find using calculus, and we'll finish it up next time.